First, I'd like to thank the organizer for invitation. And my talk will be very related to the title of this meeting. So I will talk about some applications of random matrix theory and free probability theory to get some results concerning asymptotic behavior of quantum states and quantum channels. So first, I will briefly introduce the elements of my talk. So, what I mean by random quantum states and channels. So first, I will consider in this talk mixed states. So these are Hermitian matrices with unit trace and, of course, positive semi-defined. And I will denote this the set of such states by omega n. So this will be the first thing. And another thing will be quantum channels. So I just briefly remind the definitions. So first I define what is a superoperator. A superoperator is a linear operation which transforms, let's say, square matrices to square matrices. And to define what is a quantum channel, I need a definition of what is a product superoperator, and this is defined in a standard way. So the product superoperator acts on product matrices separately, and it is extended by linearity. And to get the definition of quantum channel, which I think is very well known, the quantum channel is a superoperator which is trace preserving. So after the application of this channel, the trace is preserved, and it is completely positive. So if I extend the given operation by identity operation on any additional subsystem, I still have a positivity. So this is the standard definition of quantum channel. So these are the objects on which I will impose randomness in rather standard way. And using some techniques from free probability theory, I will obtain some results which can give some information about the geometry of these states and channels. Oh, I just wanted to say that I will work on Choye-Miłkowski representation of channels. This is it is done in this way that you act on an extended channel on a basis of the set of matrices and product with the same element of basis, and that's how you define a Choi matrix. And the theorem is that a given map is completely positive if and only if the Choi matrix is positive semi-defined, and the map is trace preserving if and only if the partial trace of this matrix is an identity matrix. So this is how I will represent channels using Choye-Miłkowski matrix. Okay, now I will impose some randomness. So this is done in a standard way. So I begin with random pure states, and by random pure states, I mean that they are the states are uniformly distributed on a unit sphere, on a unit complex sphere. So I take a uniform random element on a sphere of a size. So this x and y are just c to the power n1 and c to the power n2. So I have a large sphere. Then I make a projector and trace one of the subsystems, and that's how I will obtain a mixed state. So this is how I prepare my mixed states. And then in the case when the dimensions of the spaces are equal, then we get Hilbert-Schmidt distribution on the set of states. By Hilbert-Schmidt distribution, I mean that this is just a Lebesgue measure on the set of states. Equivalent definition is from the Ginibre matrices. This is just another way of writing it. If I consider just n times k matrix with independent complex entries with mean 0 and unit variance, but the variance actually doesn't matter here, then this definition is equivalent. So that's how I put a random measure on the set of quantum states. And on the set of quantum channels, I do a similar thing, but because quantum channels have additional constraints, which is given by this partial trace normalization, that's why I do something like this, which is called partial normalization of this G dagger of this Wishart matrix. So it can be easy to check that if you take a random independent normal matrix of this size, then this matrix provides Choi matrix of some completely positive trace preserving map. Of course, I put here dimensions n squared times n squared, but they can differ, and but this is the simplest case. Okay. So I sometimes use Choi matrix, sometimes use Yamiokowski state. This is just it depends on the normalization. So because the trace of this Choi matrix is equal to the dimension of the input system, and the trace of the J matrix is equal to 1, but sometimes it is easier to work with one, sometimes with the other. So here are the what are the constraints. So in the case of quantum states, are only these two constraints. In the case of quantum channels, in this Yamiokowski state representation, we have 3 constraints, like this. Okay. So probability distribution on the set of quantum channels is defined, as I said before, but here is just to put it in here. So I define this measure gamma. It is a map from Gini matrix onto this partially normalized matrices. Okay, so now I have defined what I mean by random states and random channels, and I will try to show some results. So first I will remind very known results concerning limiting eigenvalue distribution of Wishart matrices. If first I define just a probability measure, which has some shape, some of you are familiar with it. Why is it important? Because if we consider a random normal matrix with independent entries and consider its covariance matrix, namely Wishart matrix, and count the fraction of eigenvalues which belong to a given set, then we can define a measure on a set of real numbers because eigenvalues are real, because this is a Hermitian matrix. So this is actually a random measure, but Marchenko-Pastur theorem gives that this random measure tends almost surely to a fixed deterministic measure in a limit when the dimension goes to infinity. And this measure is defined in this way. So it has an atom at 0 and some continuous part. So this is a very well-known result, and we are somehow not maybe generalizing it, but using some techniques to show how to get measures for different matrices. Okay, so we have defined something which is called subtracted Marchenko-Pastur distribution, and this has already 2 parameters, x and y. And this is related to the distribution of 3 random variables which are appropriately scaled and subtracted. So this is the abstract definition, but maybe it is easier to note how does it, what is it useful for. So we consider two Ginibrew matrices. Everything is independent here. We construct Wishart matrices. There should be I here. Two Wishart matrices. And then do appropriate scaling and take the differences. And calculate similar, what is the fraction of eigenvalues which will end up in a given set A. So this is again a random measure, random probability measure. And by general free probability theory results, we have that this measure will tend to some probability measure. And we can actually calculate it using tools of free probability theory, namely free additive convolution. So there is just a simple application. If we consider, for example, trace distance over two such rescaled Wishart matrices, then the asymptotic limit will be given as an integral with respect to this measure as MP, subtracted Montiel-Compastor distribution. So to get the this distribution, how does it look like? We use, as I said a minute before, something which is called free additive convolution. And it is very similar to the standard convolution in classical probability. To calculate it, you can use some transforms. And using this transform, you can make a simple calculation and then invert the transform to get the result. And this can be done. The formulas are not very nice. They are quite nasty, but this is because there is a polynomial of third degree that you have to find a root, and this is the roots are quite complicated. So the formula for this distribution is a bit complicated, but here it is in most general form. So for any x and y. So this is we have calculated, and here are some plots together with Monte Carlo results. So the red curves are analytical curves, and we have done some numerics to show that we have a good agreement. So here we have the difference. For example, here we have the difference of two random quantum states, or maybe difference of two Wishart matrices, and calculate the fraction of eigenvalues which come up to a given interval, and we come up with this nice distribution. So this is just a histogram of eigenvalues, namely plotted together with this analytical form. Okay, so now we have identified this this distribution, so we can calculate some functionals using it. So first we can calculate, we take two random quantum states and calculate the limit. What is the limit of its trace distance? So it was my example before. So it is actually a calculation of an integral with so the measure have appropriate parameters, and the function is actually very simple because the trace distance, it is related to the sum of singular values. Actually, in this case, this is a sum of absolute values of eigenvalues. So in this case, we have to use only the modulus function here, and we can calculate this distance immediately from the definition of this SMP measure. Well, maybe not always, because sometimes this integral is very difficult to get analytical result, but actually in this case 1 and 1 you can do it, but in other cases the analytical formula for this integral may be difficult. Okay. Similarly, we can calculate the distance to a given to a maximally mixed state. So it is, in this case, this is just, we don't have to use the symmetric Marchenko-Pastur, only Marchenko-Pastur distribution. So this is actually just to show that knowing the limiting measure, you can calculate all sorts of things in the limit. So the distance to a maximally mixed state can be calculated with this formula, and it is done like this. And of course, we know that the distance to a nearest pure state will be 1, and the distance to a nearest boundary state, which means boundary, I mean not invertible, will tend to 0, since the smallest eigenvalue will be will tend to 0 in the limit. So here, just to show how using these methods we can say something about behavior of large dimensional set of quantum states. So here's just a plot how we believe that infinitely dimensional set of states will look like in a two-plane. So everything is in the unitary orbit. Every single, maybe not every, but almost all random quantum states will be in the unitary orbit of the state with a given spectrum, and the spectrum will be, of course, distributed according to Marchenko-Pastur distribution. The distance to nearest pure states will be equal to 1. The distance to the center, so the maximally mixed states, will be given by a number which was on the slide before. And the diameter of this orbit will be given by this number, because it is known theorem that if we consider the distance between two quantum states with fixed spectrum, then it will be maximized when the spectrum have a reverse order. So this is sometimes called Litsky theorem. So this is the diameter of this. So this is the sketch of the set of quantum states in the large dimension. Okay. And from this we can give some information concerning, for example, distinguishability of generic quantum states. So by Hellstrom theorem, we know that the trace distance is related to a single-shot distinguishability. So I mean by single-shot distinguishability, I mean to how the probability of correct guessing using optimal measurement if we don't know the input state and only should guess. And it is related that this probability is always less than or equal than 1/2 plus a half of a trace distance. And actually here can be equality if we take optimal measurement. And for large dimension, we can say that the optimal probability can be bounded always by this number. So, so for large dimensional mixed quantum states, we will not have perfect distinguishability. This is the bound that we cannot cross. Okay, there are some other things that you can calculate using these methods. For example, we can calculate asymptotic value of the relative entropy, and this can be done like this. And that's now using quantum Sanov theorem. We can say that performing n measurements on the state row, we obtain results which are compatible with state sigma. with probability decaying exponentially, and the exponent comes from this relative entropy. And we can also calculate asymptotic value of Chernoff information. And in this case, it is easy to see that due to symmetry, this minimization becomes trivial, and one have to check it only for s equal 1/2. And in this case, we get this value of Chernoff bound. And it says that performing n measurements on state rho and sigma, we get the probability of wrong discrimination, which scales in this way. And this Q star is this value. Okay, these methods actually give us a technique to calculate various asymptotic values, and some of these values were already known in the literature, some of them were conjectured, some of them, if they were proven with different techniques, so they were not using this asymptotic eigenvalue distribution, but the people were working with the distribution for finite dimensional case, and then doing some neat techniques. They were establishing the limiting value. In this, using this free probability tools, you can actually calculate asymptotic values very easily. So here are just root fidelity. To calculate root fidelity, actually, you will have to use something which is called multiplicative free convolution. This is just the multiplicative free convolution will give you the eigenvalue distribution of the product of two, let's say, positive matrices. So this is Fuss-Catalan distribution. So actually, you can calculate that the root fidelity in the limit will behave as 3/4. And from this, you can calculate the Bures distance or Hellinger distance. So actually, you can calculate a lot of things, asymptotic values of a lot of things, not finite dimensional. But actually, we argue that this asymptotic value is not very far from the value of the finite dimensional case. Here are some numerics. These bars are not analytical, unfortunately. So here are some numerics for very small dimensions, and one can see that the mean value tends quite fast to this limiting value, and the bars are not so big. So these estimates work not bad even in finite dimensional cases. Okay. And of course, these kind of techniques can be used to study entanglement in bipartite systems, because this is very similar. Entanglement in bipartite systems, for example, for pure states, is very similar to mixed states of a single system. So here are some results that the fraction of negative eigenvalues can be done. And this follows from not our result, but actually we can calculate this very easily, or we can calculate G concurrence, which is just some information about the entanglement. So this actually has also been known, but using totally different techniques, this value was obtained earlier in the literature. Okay. So now I will finish talking about quantum states and say something about quantum channels. When considering quantum channels, we were thinking mostly about Diamond norm. Diamond norm is a natural norm between two quantum channels because it is related to distinguishability of channels. And it is very difficult to calculate. Even for small dimensions, to get a value, you need to use semi-defined programming. And even for dimensions of around 20, it is very difficult to get results. So it was at the beginning obstacle for us because we couldn't even make any numerical simulations to guess the limiting value of this diamond norm. But actually we succeeded to prove the limiting value even without simulations at the first step. So first I will define what is a diamond norm. First, what is induced trace norm? So induced trace norm, it is actually for a given superoperator. This superoperator is, you can think of a difference of two channels, because if we calculate the distance between two channels, we will consider the difference of two. So this superoperator is actually a difference of two channels. And the induced trace norm is just the trace norm of the output, optimized over all possible inputs. So this is a simple definition. And the diamond norm is actually this induced trace norm by an extended operation. So we extend the operation by identity on any additional subsystem, and then we calculate the induced trace norm. So this is the definition, and as I said before, it is related to the probability of optimal distinguishability of quantum channels. Yeah, so it is a known theorem which says why this is important, and there is a nice theorem that in the case of Hermicity preserving operations. So for example, difference of two channels is Hermicity preserving. It does not preserve trace because it will always end up trace equal to 0. The output will have trace equal to 0, but it preserves Hermicity. Then it is enough to restrict this optimization at this point to a one-dimensional projectors. So this is a very nice theorem which enables to make some calculations. But as I said, there is beside this one, there is no analytical formulation for it. So it is not an eigenvalue of some matrix which come up from this phi. To calculate it, you have to use semi-defined programming. But there are some bounds, and we have actually used them. So first, there is a lower bound, which is just it is related to a trace norm of Jemiukowski matrix. So this, as I said at the beginning, this is some kind of representation of channel. So, and there is an upper bound for Hermicity preserving. It looks like this. So it is actually the maximal eigenvalue. First we take the absolute value of this Choi matrix of this difference of the channels, because this matrix is no longer positive, so we take absolute value of it. We trace out one of the subsystems, in this case the second one, and calculate the operator norm, so the maximal eigenvalue. Actually, we were very happy that we have, as an effect of this paper, we'll have a new bound. We were very happy about it, but later we found out that it was already known. It follows from a paper by John Watrous when he considered simple semi-defined programs for completely bounded trace norm, and he had actually a more general version of this inequality follows from his paper. And it's not actually our result because it was known earlier. But we are able to use it to show the asymptotic value, because this inequality is not always good. Sometimes since this value, if you look at the definition, you will see that this value is always bounded by 2. And our bound can actually be larger than 2, so it's not always good. But it turned out that asymptotically it is a very good bound, and it is tight. So we are able to show it. So how we did it? So here is just, as I said before, why this diamond norm is related. So the probability of distinguishing channel is upper bounded by this value, and this here can be equality if one uses optimal measurements. Okay, so I will just sketch the proof concerning this. So first I present the theorem. The theorem says that the limit of this diamond norm actually is again given by an integral of the same measure we have used in the case of quantum states. So I note that states differ from channels because we have this partial normalization. So it is not obvious that you would get the same result, but actually it happens that the result is the same. So the trace norm, so diamond norm between two random quantum channels of a given parameters, here is a very general definition of it, is given, this distance asymptotically is given by this. So in the case of when this dimension, when this x and y is equal to 1, we have this, the value of this integral can be calculated analytically, and it looks like this. So the proof goes like this. First we prove the convergence to a lower bound, and then to the upper bound, as you might expect. So the proof of the lower bound is actually quite simple, because we only first we do approximation of this partially normalized Wishart matrices without this partial normalization, just the standard normalization. So actually we have done this kind of approximation results, and it turned out that it is not very difficult to show that it works like this. And then actually for without normalization we can actually get the results easily. Okay. So without this partial normalization, this actually comes very easy. But together with this approximation, we get the results concerning the lower bound. The upper bound is a bit more tricky because we have first, as I said, first we have an absolute value, then we partially trace out one of the subsystem, and then calculate the operator norm, the largest singular value. So it is a bit more difficult. It involves some difficult calculations to get almost true convergence. But actually we have done it. So first, similarly, we used approximation results about this this operator norm, largest singular values. So we have managed to show this kind of behavior, and actually we have used a lemma which gives us the bound for the largest eigenvalues of this largest singular values of this difference of absolute values, how it is related to the largest singular value of a difference itself. So actually it was done in this paper. It was actually we didn't know this result. It was very surprising for us that here is a logarithmic term, because usually in matrix inequalities you do not see this logarithmic terms in terms of standard norms, but it turns out to be necessary in the case when we have operator norms here. And then we were able to prove such a big theorem, but so here I've just most general formula. So we consider here a sequence of matrices, and they grow in such a way that d1 divided by d2 squared tends to infinity. They are unitarily invariant, and this family of matrices has a limiting distribution, almost surely limit distribution of some which is compactly supported. Then, if we consider a partial trace of these matrices, then we have almost sure convergence to an identity matrix, to a rescaled identity matrix, which some scale given by the mean value of this limiting measure. So actually, this theorem gives us the result, and the proof is very technical. So we defined. So here we define some constants, and then by Chebyshev inequality we bound the maximum eigenvalue, and next we prove appropriate convergence. And to get almost surely convergence, we actually had to do very long computations to bound the variance appropriately. So actually we were able to show what is the variance of this variable, how it depends on the variance of this limiting measure mu. So this is our result, and this is how we actually prove the theorem, because there are just standard calculations, and we have obtained almost sure convergence. So this is just the sketch of a proof. Okay. And here, just to show some numerics. So this is the limiting value. This is black line. This is the lower bound and the upper bound. The upper bound, as you can see, is not so good, because it is, even for 25, it is still far away. But still, the upper bound in the limit tends to this black line, and we have the convergence here. Okay, I think I got 5 more minutes, but I already finished. So.
Okay, thank you.
Thank you very much.